In this lesson, we will first learn about characteristics of rational functions and evaluate and graph rational functions. We will learn to find equations of rational functions given their graphs, and then learn about characteristics of radical functions and evaluate and graph radical functions. Rational functions are simply ratio of two polynomial functions where the denominator cannot be zero. Let's evaluate this rational function at 1, 2, and 3. To evaluate, we simply plug in the input for all x's in the function. So f of 1 is 2 times 1 squared minus 5 times 1 plus 2 divided by 1 squared minus 5 times 1 plus 6. And we follow orders of operations to simplify it. Recall the orders of operation as parentheses, exponents, multiplication, division, addition, and subtraction. And f of 1 simplifies to negative 1/2. We follow the same process to evaluate f of 2. Wait a second. What? I thought we cannot divide by 0. Let's try evaluating f of 3 using the same process. Dividing by 0 again. Let's see if we can figure out why we keep getting 0 in the denominator for this function. Both numerator and denominator can be factored. So we get 2x minus 1 times x minus 2 in the numerator and x minus 3 times x minus 2 in the denominator. And we can see that there is a common factor x minus 2 that can be cancelled. Note that after canceling the common factor x minus 2, we need to list all restrictions. Since x minus 2 was the common factor that was cancelled, x cannot be 2. And since there is still a denominator of x minus 3, x cannot be 3. So domain of f of x is all real numbers except 2 and 3. It's because of these restrictions at 2 and 3 that when evaluating f of 2 and f of 3, we get 0 in the denominator. In interval notation, we express this as negative infinity to 2, union 2 to 3, union 3 to infinity. A vertical asymptote is a vertical dashed line of the form x equals a, where the function approaches positive or negative infinity as x approaches a. Note that the function is undefined at a, and the graph may never intersect a vertical asymptote. A horizontal or slanted asymptote is a dashed line of the form y equals mx plus b, where the function approaches the asymptote as x approaches positive or negative infinity. Note that if the slope m equals 0, we get a horizontal asymptote, otherwise we get a slanted asymptote. Unlike the vertical asymptotes, the graph of a rational function may intersect a horizontal or slanted asymptote. Here's the same function f of x we worked with earlier. We list restrictions as x cannot be 2 or 3. A restriction of a rational function is either a whole or a vertical asymptote. A rational function has a whole at a point where numerator and denominator are both 0. We can easily find this by factoring the numerator and denominator and find the common factor. The restriction of 2 came from the common factor x minus 2 that we cancelled. To find the y-coordinate of the whole, we evaluate f of x at x equals 2 using the simplified version of f of x, that is, 2x minus 1 divided by x minus 3, and we get negative 3 for the y-coordinate of the whole. So the rational function has a whole at 2, negative 3. The restriction that is not a whole is a vertical asymptote. So 3 came from the factor x minus 3, and x minus 3 was not a common factor, and it is still in the denominator of the simplified version of the rational function. So x equals 3 is a vertical asymptote. So we first factored the rational function and listed its domain restrictions, and then simplified the function and found the whole using the common factor that was cancelled, and then listed the vertical asymptote. To find horizontal or slanted asymptote, we divide the numerator of the rational function by its denominator using the simplified version of the function. So we divide 2x minus 1 by x minus 3 using the long division. The horizontal or slanted asymptote is y equals the quotient of the long division. And since this equation has no slope, the asymptote is horizontal. To find x-intercept, we set y to 0. A rational function is 0 only if its numerator is 0. So 2x minus 1 equals 0 when 2x is 1, that is, when x is 1/2. So the x-intercept is 1/2, 0. And to find y-intercept, we set x to 0. And f of 0 is 1/3. So the y-intercept is 0, 1/3. We can now graph the rational function. We start with graphing the asymptotes. Our vertical asymptote is x equals 3, so we graph a dashed line at x equals 3. Our horizontal asymptote is y equals 2, so we graph a dashed line at y equals 2. We have a hole at 2, -3, so we plot an open dot at 2, -3. The graph will go to the hole, skip the hole, and then continue afterward. Next, we plot our x and y intercepts. Note that since the graph must go through the x and y intercepts and get to the hole, there is a curve on the lower left corner. However, since we don't have x-intercepts on the right side of the vertical asymptote, the graph may not be on the lower right corner, so the graph must be in the upper right corner. This is how we draw the graph of a rational function. Note that there is always a piece of the graph of the rational function on each side of the vertical asymptote. So if there is one vertical asymptote, there are two pieces of the graph. And if there are three vertical asymptotes, there would be four pieces of the graph. Let's look at another example. First, we need to factor the numerator and denominator. The denominator is easier to factor, so let's factor that first. Factors of -3 that add up to -2 are 1 and -3. So the denominator factors to x plus 1 times x minus 3. The numerator has 4 terms, so factoring by grouping may be a good method. There is an x squared common between the first two terms, so we factor out the x squared from the first two terms, and we get x minus 2 left from the first two terms. There is a -9 in common in the second two terms, so we factor out a -9 from the second two terms, and we have x minus 2 left from the second two terms. So pulling out the x minus 2 factors in the numerator, we get x minus 2 times x squared minus 9. X squared minus 9 is a difference of squares, so we can factor it to x plus 3 times x minus 3. We have x plus 1 times x minus 3 in the denominator. So our domain restrictions are -1 and 3. Now we can cancel the common factor x minus 3 and simplify the function to x minus 2 times x plus 3 divided by x plus 1. Now for the restrictions, x cannot be -1 or 3. Since the restriction 3 came from the factor x minus 3 that was a common factor in the numerator and denominator and was cancelled, the rational function has a hole at x equals 3. We evaluate f of x at x equals 3 using the simplified version of f of x to find the y-coordinate of the hole. So this function has a hole at 3, 3/2. The restriction that is not a hole is a vertical asymptote. So the vertical asymptote is x equals -1. To find the horizontal or slanted asymptote, we need to perform the long division. Note that we always use the simplified version. To perform the long division, both numerator and denominator need to be in expanded form. So we FOIL the numerator and then perform the long division. Recall that the quotient of the long division is the horizontal or slanted asymptote. The quotient of this long division is x. So y equals x has a slope of 1, which gives us a slanted asymptote. To find x-intercept, we set y to 0. Y is 0 if the function is 0. And any rational function is 0 if its numerator is 0. And the numerator is 0 if x minus 2 is 0 or x plus 3 is 0, which we get x equals 2 or -3. So x-intercepts are 2, 0 and -3, 0. To find y-intercept, we set x to 0. An easier way to find this is looking at the constant of the numerator and denominator. When x equals 0, we have -6 over 1, which simplifies to -6. So the y-intercept is 0, -6. We can now graph the rational function using the information. Let's plot the whole at 3, 3/2, then the vertical asymptote at x equals -1, and the slanted asymptote at y equals x. Then we plot x and y intercepts and draw the curves to go through the points. In this example, we're given a graph and are asked to find the equation of the rational function. We can see that the vertical asymptotes are at -1 and 2. The vertical asymptote of x equals -1 gives the factor of x plus 1 in the denominator, and the vertical asymptote of x equals 2 gives the factor of x minus 2 in the denominator. There is a whole at 1, 3. As we saw before, wholes come from common factors in the numerator and the denominator, so we get x minus 1 in the numerator and the denominator. The horizontal asymptote is at y equals 1, which means the quotient of the division is 1. This would happen when the degree of the numerator and the degree of the denominator are the same. So we must have two other factors in the numerator. X-intercepts are -2 and 3. As we saw before, x-intercepts come from the factors of the numerator, confirming that there are two more factors in the numerator. So we get x plus 2 and x minus 3 in the numerator. The y-intercept is at 3. If we plug in 0 for x, we get 6 in the numerator and 2 in the denominator, which simplifies to 3, confirming that the y-intercept is in fact 3. And so we have the equation of the rational function for this graph. Radical functions are functions of the form nth root of a polynomial function, where n is a natural number greater than or equal to 2. The symbol is called radical, and the number inside the caret part of the symbol is called index or root, and the expression in the symbol is called radicand. Let's use f of x equals to the square root of 2x minus 1 to explore radical functions. To evaluate f of 2, we simply input 2 for x, which is square root of 4 minus 1, that simplifies to square root of 3. We can use a calculator to approximate it to 1.732. Similarly, we can evaluate f of 1 and get square root of 2 minus 1, which is square root of 1, that simplifies to just 1. To evaluate f of 0, we input 0 for x, which we get square root of -1. Isn't square root of -1 equal to I? We're not interested in imaginary numbers here. So let's find a way to set the domain restrictions so we don't get imaginary numbers. If we get non-negative values in the square root, we won't end up with imaginary numbers. So we want 2x minus 1 to be greater than or equal to 0. Solving for x, we see that x must be greater than or equal to 1/2, and the domain is 1/2 to infinity, including 1/2. To find the range, we calculate the function over the domain interval. F of 1/2 is square root of 0, that simplifies to 0. So the range either starts from or ends at 0. We also know that the smallest a square root can be is 0, so the range should start at 0. As x gets larger, the function gets larger. That is, as x approaches infinity, the function also approaches infinity, so the range is from 0 to infinity, including 0. Here's another example where we can find the domain of a function. We set the radicand 5 minus 2x greater than or equal to 0 and solve for x. We get 5/2 is greater than or equal to x, which is the same as saying x is less than or equal to 5/2. So the domain of the function is all real numbers less than or equal to 5/2. That is, from -infinity to 5/2, including 5/2. Let's evaluate the function at 5/2 to find the range. F of 5/2 is 3. So the range is either all real numbers greater than or equal to 3, or all real numbers less than or equal to 3. Because the square root is multiplied by a negative number, the function grows towards negatives, so the range is -infinity to 3. Even root radical functions have an even number in their index. Note that if the index is 2, we don't write it and read it as a square root. All even root radical functions have a restriction that the radicand cannot be negative. So to find the domain, we set the radicand greater than or equal to 0. And their graph behaves this way. On the other hand, odd root radical functions have an odd number greater than or equal to 3 in their index. Odd root radical functions don't have domain restrictions, so their domain is all real numbers, and their graph behaves this way. Here's the first example we had looked at before. We will find 3 points to graph it. F of 1 is 1, f of 5 halves is 2, and f of 5 is 3. We use these points and the domain and range of the function to graph it. We plot the start of the graph using the domain and range, and then the 3 points, and draw the curve to graph the function. Here's the second example we looked at before. We will find 3 points to graph it. F of 2 is 1, f of 1 half is -1, and f of 5 is -3. We will use these points and the domain and range of the function to graph it. We plot the start of the graph using the domain and range and the 3 points, and then draw the curve to graph the function. Let's look at a cube root function. Odd root radical functions don't have domain restrictions, so the domain and range of the function is all real numbers. We strategically choose x values to evaluate the function at, so we can simplify the cube root. We choose -6 so that the radical becomes 2 minus -6, which simplifies to cube root of 8 that can be simplified. And we get f of -6 as cube root of 8, then plus 1, which simplifies to 3. We chose a number to get a cube root of 8. Now we choose a number to get a cube root of 1. If we choose 1, the radicand becomes 1, so we evaluate f of 1. If we choose 2, the radicand becomes 0, which has a perfect cube root, so we evaluate f of 2. And we get perfect cube roots when x equals 3 or 10. So we evaluate f of 3 and f of 10. We then use these points to graph the function. We plot the points and draw a curve through the points.